back, Algebra 2 students. Today we have section 2.2, inverse variation. So last class we went through direct variation, where the input and the output both change in the same direction. So if the input increases, then the output decreases. So the inverse variation is basically the opposite of that, that as the input increases, the output is going to decrease. So what that's going to look like is if I have input is x and the output is y, then the inverse variation function is y equal k over x to the power of n. And if this is the relationship, we're going to say that y varies inversely as x to the n power. In other words, the x to the is in the bottom of the fraction and the y is over in the top. So they're in different positions, whereas in the direct variation we had y equal k times x to the n, where x was in the same line as y. The other way we can say this is y is inversely proportional to x to the n. So either of those, either y varies inversely as x to the n or y is inversely proportional to x to the n, it's the same, two different ways to say the same thing. So let's look at a application problem. So Ren and Stimpy, a really old cartoon. It's a good one though. Ren and Stimpy are trying to balance on a seesaw. For you guys that don't know, Ren is kind of a little chubby cat-like creature, and Stimpy is a kind of skinny rabbit. So they're trying to balance on the seesaw, and Stimpy is the chubby one, and Ren is the thin one. So Stimpy weighs 55 kilograms, and he is sitting 2 meters from the fulcrum, which, as you know from your physical science class, the fulcrum is just the center of the lever. So basically, it's going to be the middle. So Stimpy weighs 55 kilograms. He's sitting 2 meters from the center, the balance point, the fulcrum. And then Ren, who's the rabbit, he only weighs 50 kilograms, so he's lighter. And the question is, how far away from the fulcrum, that balancing point in the center, how far away from the fulcrum should Ren sit to balance? Okay, so we get a little more information here. So how far away from the fulcrum must Ren sit to balance with Stimpy? So we get a little more information, which is the weight of the person, the distance from the fulcrum. The distance from the fulcrum varies inversely with the weight of the person. So we're going to take those words and translate it into the equation. So we know how the varies inversely equation works. So let's identify our variables. So we can have the distance from the fulcrum, so we'll just call that d, and it's going to vary inversely with the weight. So the weight we'll just call w. So basically we're saying d varies inversely with w. So that means we have d equals k over w. Because it varies inversely, I'm going to put the w in the bottom, and the d is going to be on the top, on the other side. Okay, so to figure out how far Ren needs to sit, we need to figure out this k, this constant of variation. And we can do that because we know that if the weight is 55 from Stimpy, that he has to sit 2 meters. So we can plug those in. 55 for the weight, 2 meters is the distance, and then we can solve for the k by just multiplying 55 on each side, so it's going to cut. And k, our constant of variation, is 2 times 55, which is 110. So again, that k is a constant, it doesn't change, and it's the constant of variation because it's a variation equation. So now that we know K, we can put 110 in for K, and we need to know how far away Ren needs to sit if he weighs 50 kilograms. So start off with distance from the fulcrum equals, well, now we know what the K is. It's 110 over the weight, which we know is 50 kilograms. And we can solve for the distance. It's going to be 110 divided by 50, which is 2.2 meters. So box that for the final answer. Basically, Ren has to sit 2.2 meters from the center. And you might have seen this before when you have two kids on a seesaw. The heavier one has to sit closer to the center, okay, to balance out. And the lighter one needs to sit farther away from the center. So in this case, you have the seesaw here. The fulcrum is where it balances in the middle. So you have Stimpy, the little kind of chubby cat character. So I'm going to try and draw him here. So, boy, this is really bad. You can look up these characters, Ren and Stimpy. You'll see that they look nothing like what I'm drawing here. But Ren sits 2 meters from the center, and Stimpy is the thinner character, the rabbit. And because he's lighter, he's only 50 kilograms, he has to sit farther away from that center point, the fulcrum, in order for it to balance. If he were to sit the same distance, if he were to sit 2 meters, the seesaw would tip with Ren, the heavier one, going down and Stimpy going up and getting launched off the seesaw. So for that to balance, that distance has to be 2.2 meters for Ren to sit. Okay, so I'll do one more example. The weight of a person or a body above the surface of the earth. So if you are in outer space, basically you're above the surface of the earth, the weight varies inversely as the distance, as the square. Actually, it's as the square of the distance, as the square of its distance from the center of the earth. Now, you guys know this because you know that, astronauts, the reason they can float, well, one, you don't have gravity, and two, you weigh a lot less the farther away you're from Earth, because gravity isn't applying that force that creates your weight, essentially. So the farther away you are from the Earth, the lighter you're going to be. So they go in opposite directions, the weight and the distance from the center of the Earth. Okay, so let's get to the problem. So if Axarapak, the astronaut, Axarapak, there's no one else in the class whose name starts with A, so you're the astronaut, weighs 65 kilograms, which I know is probably way more than you are, so just go with the problem. If Axarapak, the astronaut, weighs 65 kilograms on the surface of the Earth, what will she weigh if she's in outer space 18,000 miles above the Earth's surface? Okay, so let's draw a picture to get a sense of what's going on here. Always a good idea to draw a little picture. Doesn't have to be super detailed, just a nice sketch. Oh, one thing that I need to give you to solve this problem is you want to know the radius of the Earth, so how far it is from the surface to the center, and it's about 4,000 miles. So I'll give that information to you. Note, the radius of the Earth is 4,000 miles, about, roughly. Okay, so I'm just going to try and sketch what's going on. So here's the Earth. So I'm going to draw that. North America, South America, Europe, Asia, Africa. All right, so there's the Earth, and here we're going to have Axarapak in outer space. So we'll measure this. We know the radius of the Earth is 4,000 miles, so I'll draw that in first. Okay, so this radius from the center to the surface is 4,000 miles. Then we know Aksarapak is chilling out there in outer space, 18,000 miles above the surface. So we'll draw her there. She's got her astronaut's backpack on and the helmet, and she's having a great time up there in outer space. And the distance from her to the Earth's surface we're given is 18,000 miles. Okay. So let's see. We're told the weight of the body, so the weight could change, so we'll call it W, varies inversely as the square of the distance. So the square of the distance I'll call d squared, and we set up the inverse equation. Weight, W, equals inversely proportional to d squared. So equals some constant k, which we don't know yet, over d squared. So this is the setup. So I want to know what W is when d is well, it's actually going to be 22,000 because it's 18,000, because it's inversely with the distance squared from the center. So I have to measure from the center. But the thing is, I don't know K yet, but I know that she weighs 65 kilograms when she's on the surface, which is 4,000 miles from the center. So I can use that pair. I can use the 4,000 mile distance from the center with the 65 kilogram weight, because that's how much she weighs when she's sitting on the surface. And I can use those numbers to plug in for W and D and figure out what K is. So K is 1,040,000,000 when I just do the math to figure out K. Now, once I have K, I have an equation where you can put in a distance and figure out the weight. So the weight equals, we know what the K is, 1,040,000,000 all over the distance from the center squared. And we want to know how much she's going to weigh when she's 18,000 miles from the surface. Now, I have to be careful. When I first did this, I put 18,000 in for the distance, but the weight varies from the distance from the center. So I can't use 18,000. It's 18,000 plus the 4,000 that comes from the surface to the center because of the radius of the Earth. So I actually have to put in 22,000 for the distance. So it's going to be, again, 1,040,000,000 over 22,000 squared, and just put that in your calculator. You're going to get 2.15 kilograms, and that's why you see the astronauts weigh so little when they're up there in outer space. As you can see, this person would only weigh 2 kilograms, even though they weigh 65 kilograms on the Earth. Thank you very much. We'll see you in the next class for another exciting chapter of math.